So we're looking now at section 20.2.8, and for the next at least 3 lessons, and it may even be 4, what we're going to be doing is just solving problems involving Newton's second law of motion. Newton's second law of motion, of course, is the formula that's given on your screen right now. Acceleration equals net force over mass. A lot of the time, though, what we're going to be doing is using this form of Newton's second law of motion. And we will be stating the direction by looking at the question. So what I am getting at is it's like when, I think it was Mackenzie said that the net force acting on the box on the ramp was negative 74 newtons. We do not want to use positives and negatives in formulas over the next few days unless it's a kinematics formula. So this formula here, which is Newton's second law of motion, is simply talking about the magnitude of the acceleration being equal to the magnitude of the net force divided by the mass. And that's the same as this formula, by the way. Okay, so today what we're focusing on are problems involving vertical motion. And I know what's going to happen here, everybody, so be very careful and cautious about this. Because if I gave you this question right now, most of you are going to get it wrong. Okay, let's read this question and talk about it for a minute. A person and an elevator have a combined mass of 600 kilograms. The elevator cable exerts an upward force on the elevator of 750 newtons. 7.5 times 10 to the 3 is 750. No, it isn't. 7,500 newtons. So we've got a 600 kilogram mass. This is 600 kilograms. We can also use the EE notation in your calculator. And this is 7,500 newtons. And if I said to you, find the acceleration, I know what some of you are going to do. You're going to say, well, there's a force and there's a mass. And I know that force equals mass times acceleration. So you're going to end up saying that the acceleration is the force divided by the mass. Now, what I've just written, even if I do this, what I have just written is flawed. That is not a formula on your formula sheet. Does it? Oh, really? The number is different? Okay. So you have 6,500 or 6,500, not, okay. That's easy enough to fix. Thank you for catching that. So this formula that I've written, everybody, is wrong. And I can't stress this enough. That is not a formula on your formula sheet. The formula on your formula sheet is this. Now the question is, what's the net force? Just stop for a second and take a look at something that's in your surroundings. Maybe there's a box on a floor, or maybe you can look at your computer tower or your monitor. If you apply a force upwards on that object, is it a guarantee that it's even going to move? And the answer is no. You have to apply a force upwards that's at least bigger than the force of gravity downwards. That's why you can't lift the truck off of the ground, even though you apply a force. So when you do these problems dealing with Newton's second law, you must always draw a free body diagram. So that's our starting point. There's the elevator. There's a person inside of it, but it doesn't matter. And we draw all of the forces acting on the elevator. There's also a cable, right? There's a cable that the elevator is connected to. You're told there is a force upwards of 6,500 newtons. Now, is that the only force acting on the elevator? Well, no, because gravity is there. So there's a gravitational force down. Now, I want to be careful about something here. I don't think we should draw the force of gravity down. I think what we should do is calculate the force of gravity first. So this force up top is the applied force. There is a force of gravity acting down, and that's going to be equal to a certain number of newtons. We have to calculate that. And the reason we're going to calculate it is, think about this for a second. What if we got 8,000 newtons for a force of gravity? If the force of gravity were 8,000 and the elevator is being pulled up with 6,500, the elevator wouldn't move. So we have to calculate that on the side. There's a little detour that we take. We calculate the magnitude of the force of gravity by taking the mass times 9.81, so that's 600, multiplied by 9.81, which gives us 5886. The force due to gravity is about 5,886 newtons, which means since the applied force upward is 6,500, the force of gravity down is a little bit less. And I'm going to exaggerate that just so you can see it visually. It's not that much less, but it's 5886 newtons, which is less than 6,500. So the net force, and this is going to be the thing that is going to be most challenging for some of you, is to just slow down and say that anytime you want to use this formula that's in red on your screen, you have to look at this free body diagram and say to yourself, what is F net? Because F net is the thing that goes into the formula that's in red. And in this particular case, the net force is the applied force upwards minus the force of gravity downwards. That's going to give us how many newtons of net force upwards there are. So this is going to be 6,500 minus 5886. This is going to equal F net, the magnitude of F net anyway. So we get 614 newtons. The net force is only 614 newtons upwards. So this is what I talk about when I say we don't put positives and negatives in. We just throw in the direction when we need to think about the direction. Now we can use the red formula. The acceleration will have a magnitude of the 614 newtons divided by the mass of 600 kilograms. So it's 1.02 meters per second squared upward. And I will tell you right now, everybody, I mean, this is one of these things that I wish I could figure out the way to teach it so that nobody would ever make a mistake. But I know for a fact that if I throw this on an exam, some of you are going to look at it and say, oh, wow, this is one of those easy questions. I need to take the force and divide by the mass and get this number. And believe me, if it's a multiple choice question, that will be a choice. That's wrong. It's not any force divided by the mass, it's the net force. Before we move on with the next example, any questions with that one? All right. The next one, what's the applied force required to accelerate a 250-gram model rocket with an upward acceleration of 32.4 meters per second squared? So we've got a rocket. It's firing out all this fuel, and as a result, the rocket goes upwards. Now, if the rocket accelerates upward, then what that means is that the upward applied force on the rocket must be smaller than the gravitational force on the rocket. I'm going to get rid of this fuel. It's just getting in the way of my explanation. So if I label the forces here, I have a force due to gravity and an applied force. So what you're going to discover, well, if we were in school, what you're going to discover is if you do an example like example 2, I'm just throwing up example 1 for a minute here. If you do an example like example 2 and you get the wrong answer, let me know, Taylor, when you've got them. So you do an example like number 2, thank you, and you get the wrong answer, and I look at your work. If I don't see what I've just drawn, that will be my question to you. Where is your free body diagram? I mean, if you can get the right answer without a free body diagram, that's great, but most people need it. So now what we do is the following. This is how I would recommend doing these problems from now on. You start off with F net, the magnitude equals ma. And then what we're going to put in for F net is the magnitude of the applied force minus the magnitude of the force due to gravity. Because that's how you would add those two forces. You would add the two forces by subtracting the numbers because they're in opposite directions. And because we're subtracting, you don't put negatives in for anything. We're already taking care of that. And this is going to be the mass times the acceleration. So we can calculate these. Well, the applied force we know. Well, we're trying to find the applied force, actually. The force of gravity is mg, which is 0.25 kilograms. We need to work in kilograms, times 9.81 meters per second squared. Okay, let's calculate that. .25 is the mass times 9.81 gives me 2.4525. So what we end up with is the applied force upward minus 2.4525, I think. Double check that. Equals the mass, which is 0.25 kilograms, times the acceleration, which is 32.4 meters per second squared up. So this, I want to be very clear. This formula here is only for a situation where you're applying a force upward to an object to accelerate it upwards against gravity. But we can calculate this now. We've got a simple formula. The applied force will be equal to the magnitude of the applied force is going to be equal to that 0.25 times 32.4 plus, we have to add that 2.4525 to the other side. 0.25 times 32.4 plus 2.4525. So about 10.6 newtons. So the applied force would be 10.6 newtons up. I'll leave that up there for a minute while I ask you to look over your work for example 2, this example, and see if there are any questions about it. I should have done this earlier, but while I'm leaving it up right now, can you do me a favor and just do the old too fast, too slow, just right? I should have asked this part earlier, but I just want to know how it's going. All right, that's good to hear. So any questions with this example now? All right, we're going to move on and take a look at the next question. A skydiver jumps out of an airplane. During the first few seconds of one jump, the parachute is unopened, right? You don't jump out of a plane and immediately open your chute. While the person is falling with their chute closed, the magnitude of air resistance on the skydiver is 250 newtons, and they are accelerating at 5.96 meters per second squared down. So I know they look like some kind of ant or animal falling, but there's the skydiver, and the hair is flying up. This is the chute that's strapped on their back. And they're accelerating down at 5.96 meters per second squared. Now, just a second here. If they're accelerating down at 5.96 meters per second squared, that's smaller than the acceleration due to gravity, but there is still a gravitational force pulling them down. So why are they not accelerating at 9.81? Because there is an opposing force, which is the force of friction between them and the air. So this is our free body diagram. What we have is the force of gravity and the force of friction. You're told the force of friction is 250 newtons, so you know what that actually is. We don't know the force of gravity. We're going to build an equation. We're going to say, looking at this, the net force has a magnitude of the force of gravity of its magnitude minus the force of friction, its magnitude. See, I don't believe that there's very many people who can read the words and get this formula. I really don't. And I want to point out to you that if you look at that formula that I'm highlighting for example 3, it's different than the formula that we were highlighting for example 1, or 2 rather. In example 2, the net force was the applied minus the force of gravity. In example 3, the net force is the force of gravity minus the force of friction. So I will tell you something that I may have mentioned before, but I talk about a lot with my physics 30s. Students who do well in high school physics do so because they see the bigger picture. They look at physics principles. And the physics principle here is the idea of net force being found from a free body diagram. Students who memorize a formula, like MA equals applied minus force of gravity, are not going to be as successful because not all questions use that formula. We have gone away now, all of a sudden today, we've gone away from finding the right formula on your formula sheet to get the answer. And instead, we're building the right formula. So I'm going to pause there before we throw some numbers in, because the rest of it is math. It's not even physics. Does anybody have any questions regarding that setup, the free body diagram, or the fact that to find the net force, you would subtract those two forces? Okay, so how do we find net force? Net force is MA. I've just written out what this is equal to. This is now equal to mg, which is the force of gravity, minus the 650 newtons force of friction. And I have mentioned this to you before, you really have to know the difference between A and G. They're not the same. A is the physical acceleration of the object, G is 9.81. So now let's put in the other numbers that we know. We know A is 9.81, so we end up with the mass times 9.81 equals the mass times 5.96 equals the mass times 9.81 minus 650. So I'm going to write this as it would appear in math. 5.96 m equals 9.81 m minus 650. Is it only 250? It is only 250. Thank you. I'll change those to 250s. Thank you, Sienna. I don't know where I got 650 from. I think it might be from a previous question. Anyway, it's minus 250. So we have 5.96 m equals 9.81 m minus 250. M stands for mass here. So to solve this, I'm going to add 250 to both sides. If you know how to solve this, fine, you're done. I'm going to add 250 to both sides and end up with 5.96 m plus 250 equals 9.81 m. Now I can subtract 5.96 m from both sides. So this is a rare situation where you have a variable you're trying to find, m, but it appears in two places. I end up with 250 equals, and we have to subtract these two numbers. (9.81) minus 5.96. 3.85, so we get 3.85 m. And now to find m, you divide both sides by 3.85. And we're going to get our mass. So the mass of the skydiver and the chute that she is carrying is 65 kilograms. While I am just giving everybody a second to make sure that you are caught up before we finish off this lesson, it's important that you draw your free body diagram and build your F net equals MA from that. Any questions with example 3? All right, let's move on. I believe there's one more example and it's got an A, B, C to it, but I want to talk in general about elevators. So we're going to be drawing some free body diagrams here. Here's an elevator. There is a cable running through the elevator. in some way so that the elevator can move up and down in a straight line. And that's the diagram of the elevator we're going to draw in each of these three questions. So we know the mass, we'll get back to that. We want to find the tension in the cable. The first thing that you have to be aware of is the word tension means applied force. So whenever we talk in the real world or the engineering world or the physics world about tension, we're talking about an applied force. Now clearly, I hope you understand that the force applied to the elevator by the cable must be upward. If the force that the cable exerts to the elevator were downward, then we would have a disaster on our hands. Now, if the elevator is accelerating up, I hope it's clear that the tension in the cable must be greater than the force of gravity. I mean, think about that for a second. I'm going to label these. This is the applied force. This is the force due to gravity. And what I am telling you, and I want you to think about this and make sure that it makes sense to you, is if it's accelerating upwards, then it has to be the case that the applied force upwards has a larger magnitude than the force of gravity downward. Whoop. Do that again. There we go. That the applied force upwards must be greater than the force due to gravity downward. It accelerates upwards, so the net force has to be up. Moving ahead, before we even do any calculations here, and we take a look at B, I hope it's clear that since it's accelerating downward, in B, the applied force upward must be smaller than the force due to gravity. And that's something that is always going to be the case. If it's accelerating downward, then it must be the case that the applied force up is smaller than the force due to gravity in magnitude. Now, before we move on and talk about C, let's talk about these in more detail. If the elevator is accelerating up, that means the net force is up. And looking at this diagram, the net force would have to be found by taking the applied force and subtracting the force due to gravity. Because when you add vectors that are in opposite directions, you take the bigger minus the smaller. So if it's accelerating up, then this is what you can apply. And I'm starting to get the feeling here, I suppose, that many of you would understand that you take the force of gravity away from the applied force to get this formula without having to draw the free body diagram. In this particular case, the result is that when you look at this diagram, what you're going to say is that the net force can be found by taking the force of gravity, which is bigger, and subtracting the applied force. So I want to pause there. And ask, if that makes sense to you. Don't worry about this. This is that if the elevator accelerates up, the applied force up is greater, so the net force would be applied force magnitude minus force of gravity. But if the elevator accelerates down, it would be the other way around. Okay, well, if it does, then all we have to do is use this formula F net, which is ma. So we have ma equals the applied force up, which we are trying to find, minus mg, which is the weight or force of gravity down. Whereas over here, we're going to have ma equals the tension in the cable, the applied force, taken away from the force due to gravity. And I'm always kind of a little flabbergasted by this. By the way, we're going to go a little bit longer here, but that's okay. I'm always a little bit flabbergasted by this because some people look at that and go, you mean to tell me if I subtract it the other way, it makes a difference? And the answer is yes, it does. So we are going to put in the mass, which is 3,200 kilograms, times the acceleration, which is 2.5, equals the applied force, which I'm just going to call the tension. It's the tension in the cable. Let's call it T, minus 3,200 times 9.81. So to get our answer here for this question, we are going to have to take this 3,200 times the 2.5 and add the 3,200 times the 9.81. So we're going to get a tension that's equal to 3,200 times 2.5 plus 3,200 times 9.81. Don't worry about calculating it just yet. You can calculate it if you want, but I'm going to now talk about the next one. The next one would be 3,200 times the acceleration. In the second one is 3.5 equals 3,200 times 9.81 minus the tension in the cable. So when we solve this for the tension in the cable, right now it's negative. I'm going to move that t to the other side, and we will get the tension equals 3,200 times 9.81 minus 3,200 times 3.5. So now let's calculate both of those, please. We're going to calculate what the tension in the cable is for A, this is question A on the left, and for B, which is on the right. I get 39,392 newtons for the tension in the cable for question A. Before we just talk about B and then wrap this whole thing up, anybody else getting that same number? Okay, so that's, the numbers are okay. And for the other one, I get 20192. So this is the tension in the cable when the elevator is accelerating down. And I'll just ask the same question. Anybody else getting that number? So the bottom line here I'll just leave the answer up here in case you need to look at it. The bottom line is if the elevator, oh, that's stupid. There we go. If the elevator is accelerating up, then the net force has a magnitude that's equal to the applied force up minus the force due to gravity down. But if the elevator is accelerating down, the net force, which is ma, has a magnitude of the gravitational force down minus the applied force up. It depends which one is bigger. Now, with that in mind, I'll let that sink in for a minute. If the applied force up is bigger, it accelerates up. If the applied force down, which is the force of gravity actually, is bigger, then it accelerates down. So now what I would like everybody to do is think about C. What if the elevator is moving up at a constant speed? My question to you is the applied force up bigger than the force due to gravity down in magnitude? Is the applied force up smaller in magnitude than the force due to gravity? I want everybody to be very cautious here about not being impulsive and picking an answer. I want you to think about the question, read C very carefully in terms of what it says. And the question is the first statement true or is the second statement true? And that's correct, Cole. It's neither. Some of you are going to say that even though there's no acceleration, by the way, constant speed means no acceleration. Some of you are going to say, I know they are equal. I know that there's no acceleration, so the forces are balanced. But if it's moving up, doesn't the upward force have to be a little bit bigger than the downward force? And the answer is no. We've had this conversation before where I talk about a car moving down the highway at 140 kilometers per hour. There is a force forward applied by the engine, and there is an equal but opposite force backward that is due to friction. If the force forward were greater, the car would be speeding up, and it's not. So the answer to my question is that neither of these are correct. This is false, and so is this. What's true is that the applied force upward has a magnitude that's exactly equal to the force of gravity downward. So to find the tension in this cable, all we have to do is find the weight or the force of gravity acting on the elevator. There's no MA to it because the acceleration is zero, the net force is zero, and if the net force is zero, the force is balanced, which means that the tension must be exactly equal to mg. So all we have to do to find the tension in the cable is take the 3,200 kilograms times 9.81 meters per second squared. What we are finding is the weight of the elevator and the person. So we're finding the force due to gravity. But because of our free body diagram, which now wonder if I still have it in my page. Yeah, I do. Which now the free body diagram for C it looks like this. Those two forces are exactly equal. So when we find Fg, we will have found the tension. So the answer to the question is 31,392 newtons. And again, what we ended up doing here today is all about vertical forces. But this is just one part of using Newton's second law. We're going to be looking at inclined planes. We're going to be looking at pulley systems. If you do not have a free body diagram to look at, then it may be easy to make a mistake and not know what to do with all the forces. We've elevated things up to a higher level all of a sudden. So the class officially ends now because they said 2-hour periods. I'm, of course, here till 11:30, which is when we would normally go to. Your homework are the problems set out here. I would focus mainly on problems 1 to 5 that are attached. If you were to get those done and not have any problems, then I'm happy.